Good day and welcome to theme 3.6, where we will be discussing parametric surfaces and their areas. So previously we've discussed parametric lines or curves, one must say. So in a curve we had one parameter that we specified, which was t. But for surfaces we need two parameters. So the general equation for a surface parametric equation would be r of uv. So those two parameters can be anything. It can be cylindrical parameters, it can be spherical parameters, theta, r, theta, and phi. We'll get to that later. But what's important is that you need to get x, y, and z in terms of those parameters. And very important, we have to specify the boundaries of these parameters that we are using to describe our surface with, because we will later use it for integrals to actually get these areas of our surfaces. So some examples of how to actually parameterize our surface. So let's say find the parametric representation for the sphere x squared plus y squared plus z squared is equal to 16. So we know that rho squared is equal to 16, so rho is equal to 4. So x we know is rho cos theta sine phi. So since we have rho, we have 4 cos theta sine phi. Y is equal to 4 sine theta sine phi, and z is equal to 4 cos phi. And then we have our parameterization of our surface. It's not that difficult, is it? But one more thing, we need the boundaries of theta and phi. So if we look at this, this is the top half of our sphere, which is an entire sphere, and we know that it is completely round. So our theta will go from 0 to 2 pi, and our phi will go from 0 to pi. If it was a hemisphere, you would have phi going from 0 to 2 pi over 2. Find a parametric representation for the intersection of the paraboloid z is equal to x squared plus y squared and z is equal to 16. So we have an intersection here, which is a surface. So it's just a flat, like, circle at z is equal to 16. So the first method you could use is you can turn it into cylindrical coordinates. So you can say x squared plus y squared is equal to r squared. So we have x is equal to r cos theta, y is equal to r sine theta, and z is equal to r squared. And then you would have a parameterization in terms of r and theta. And you can specify that r goes from 0 to 4 and theta goes from 0 to 2 pi. The next method that you could have followed is you could have said, well, z is equal to x squared plus y squared. X is equal to x, and y is equal to y. It's much like the function analysis that we took for line integrals, where we said x is equal to t and y is in terms of t. But in this case, we're just using x and y as our parameters. And then you would have a parameterization in terms of x and y, which will then be x, y, and x squared plus y squared. So now we need the boundaries of x and y, and that you can get by using your typical boundary problems. So x is between negative square root 16 minus y and positive square root 16 minus y squared. And then y is just between negative 4 and 4. So that is the method 2 that you could have used. Next up on the agenda is tangent planes to a surface. Okay, so a plane at a point with a position vector r that contains the tangent vectors r mu and rv, and have the normal vector r mu times rv. Okay, so this just says, okay, this is the plane that you have. It has a positional vector. It starts at a certain point, and what you need to get a tangent plane is you need to get a normal vector and you need to have a point on your plane. So this we get from the surface that it is tangent to, and this we use to get our normal vector. So in an example, they ask us to find the tangent plane to the surface with parametric equations. So they give us the parametric equations of x is equal to u squared minus v, y is equal to u plus v, and z is equal to u. The plane passes through the point -3, 5, and 1. So this is x, y, and z on the plane. So first thing we need to do is we need to get a normal vector, which we can do, but we first need to find u and v so that we can have the normal point on the plane. So now that we have a point where the tangent plane exists, which is 1 and 4, how we got there is we said that, okay, x is -3, but it's also equal to u squared plus minus v. And then y is equal to 5, which is equal to u plus v, and then z is equal to 1, which is equal to u. And then we got that v is equal to 4. And then that would be our positional vector that we find. Next step would be to get ru, so the partial derivative towards u, which is the following, and then the partial derivative towards v, and then if we get the cross product of those two, this is our cross product and this is our normal vector. But we need the normal vector in terms of numbers. So that's why we went into the trouble of getting u and v. So we just plug in u here, and that will give us our normal vector to the plane. So we have our normal vector and we have a point on the plane. So this is how we use it. So we say x minus -3, y minus 5, and z minus 1, dot producted with our normal vector is equal to 0. Because we know that if you have two perpendicular vectors dot producted, it will be equal to 0. A vector on the plane and the normal vector to the plane will be equal to 0 if dot producted. And then you just do a dot product and you get your equation of your tangent plane. Next up is surface area. So now we actually can get our surface area of our parametric surface. So what we've gotten before now is just how to parameterize a surface. But now what we want is actually the surface area. So let's say we have a surface like this. We want to know, what is the surface? What is the area of all these small little blocks? So how we get to that is we parameterize our surface and we have our boundaries, and then our equation for our surface of our area is the following. So you partially derive your parameterized equation towards the first and then the second parameter. You then cross product them and you take the magnitude of that. And then you have a dA and d. So this d is dependent on these parameters. Where do they exist? Let's say these parameters were theta and phi. Then you'd have the boundaries of theta and phi for your surface, and then you'd use them for the integral. Let's have an example. So the example asks us to find the surface area of the hemisphere of x squared plus y squared plus z squared is equal to 16, where z is greater than and equal to 0. So it's just above the xy plane. First thing we do is we parameterize the plane or the area. So we know that rho squared is equal to 16, so rho is 4. Then we can write x, y, and z in terms of theta and phi, and it's parameterized. So then we have a parameterized equation that looks like this. And we have our boundaries, because we know it's a sphere, so theta is between 0 and 2 pi, and we know that phi, since it's a hemisphere, only goes from 0 to pi over 2. But now we have our boundaries. But what is the cross magnitude of the cross product of the partial derivatives towards phi and theta? So first we do the partial derivatives. So we partially derive it towards phi, which would give us the following. And then we partially derive towards theta, which gives us this. And then we cross product them, which leads us to the following components. And yes, these are our following components that we get for our cross product. Now we want to get the magnitude of this cross product, which will just be the square root of all of this. And we will end up having 16 sine phi, which is equal to 4 squared sine phi, which also can maybe remind you of our integrating factor that we had for a sphere. But yes, that is how you would get to this. And then you add everything into your integral. So you have your boundaries of theta and phi, and you have your magnitude of your cross product, and then just d phi, d theta, and then you can just integrate that and get your surface area. So sometimes we have a parameterization that just has x equal to x, y equal to y, and z is equal to f of xy. In that case, you'll find that your partial derivative towards x is just 1, 0, and f of x, and partial derivative towards y is just 0, 1, and f of y. If we get the magnitude of that, it ends up looking like this. And then if we want to get the area, it looks like this, and this will be dx dy, and these will be boundaries of x and y. Sometimes people learn it off of heart that it looks like this, but I would advise to not use it as a rule of thumb, because it's not always parameterized in terms of x and y. So just if you have x and y, you can just do the normal steps of getting your partial derivatives towards x and y, and then getting the magnitude of your cross product. So that is how you get surface area.